What we'll discuss today is the next lecture. I thought this was an interesting lecture because it kind of summarizes everything we've done to this point and kind of sets up what we'll discuss in the remaining 4 to 5 sections of the course. I thought it was very instructive, especially because it refreshes what we've been doing for quite a while now, and then at least from my perspective, compares and contrasts the techniques, which in some sense is, from a practical standpoint, quite useful of when to pull out which of the techniques we've seen, what are its advantages and disadvantages, and interestingly, from a, if you want to work in that space kind of perspective, what's left to be done and what are challenges remaining in that space or in that particular approach that need further evaluation. So that's kind of the focus. I think this time, I hope that we can finish it in one session. So hopefully we'll be done with this entire lecture within just today, and that'll help us kind of keep things on track. I'll touch on a mistake I made in the schedule, so towards the end, and if I forget, please do remind me. Okay, with that said, let's start kind of looking at the various strengths and weaknesses of the various techniques that we've looked at so far in the course. But before we do that, an interesting setup kind of comment by Jeff Hinton about, how many synapses we actually have in the brain, and on the average, how long a human being lives. And from that, he says, that obviously there must be a lot of unsupervised learning going on, because the only place where we get, the only way that we can get kind of the synapses divided by the seconds, that is the number of inputs, or is the sensory system, if you will, and the perceptual system. And actually, for other reasons that I won't bore you with, but I've kind of been interested in this term he uses of proprioception, which is, you can look it up on Google, and it's a very fascinating dimension of our awareness, which is our awareness of our body in the world, if you will. And the reason we got interested in it originally is because some people, for whatever reason, very strange disease, they lose their sense of proprioception, which means they lose their sense of where the body is in the world, their own body, which makes any movement that they do extraordinarily difficult, because they have to think about it and move the arms and legs, which is not what the average human being does. We do it thoughtlessly in a sense, or we do it because of the sense of proprioception that we have. But sometimes for very strange reasons, people lose that sense, and it's a extraordinarily hard disease to deal with, because that means you have to think about every movement that your body makes. You can't just say, oh, I want to speak, so let me pick up the phone, and you just do it. So it's a fascinating topic by itself, but including that and all the other external senses, he kind of points to it. So the other takeaway, I don't know, that I took away is, we are definitely an over-parameterized system in general, and it probably need to be that way in order to deal with a variety of inputs that we get, both sensory and otherwise, and adapt. So anyway, that's kind of the sense setup, not directly relevant, but interesting comment. And then he gives a very quick summary reminder of all the course topics we have covered. We started with the autoregressive models. If you recall, we started with MADE, and we'll go through each of these in much greater detail, but just a quick reminder, we started with the autoregressive models. Here are the various types. that we looked at, and then we moved on to flow models, and here are the various improvements and types that of flow models that we dealt with. And then we switched from the autoregressive and flow space to the latent space. And these are the latent variable models, approximate likelihood. We discussed how to calculate the variational lower bound. The one thing I don't recall is I believe he just mentioned that wake sleep was something that was in existence before autoregressive models, but I don't believe that we actually discussed wake sleep. I recall him saying just that wake sleep is a prior technique, so I don't think this was covered by the course in any detail, but again, this is no longer in use and kind of a legacy method, if you will. We discussed autoencoders, important weighted autoencoders, pixel VAEs, and then variational quantized variational autoencoders. These are all the latent variable models that we discussed, and then we moved to the implicit models, which are basically generative models. And within generative models, we also focused just, or at least when introduced to moment matching, and then I wouldn't say energy-based models, it was mostly energy-based explanation of GAN models, which help us understand kind of the rationale behind GANs. And then the last lecture was on self-supervised learning, which helps us learn representations from raw sensory observations. And we saw the different techniques. Underlying it is how do we deal with data, combine it with compute, and then if you go from core cognitive principle, especially invariance of the priors, what kind of common sense task, the jigsaw solving, the rotations, and then the advanced things like CPC version 2, MOCO, and Sinclair that we discussed. So that's kind of the summary of the course, if you will, in one slide so far, although each of these took us many hours to get through. So first, let's look at the autoregressive models, and you'll see that the template he uses is a fairly interesting one. Just kind of discuss where these methodologies started, where we ended up with the method, what kind of improvements were made along the way, what's positive about it, what are some of its challenges, and then what future work remains in this space for somebody interested in pursuing that domain. So the other interesting thing is if you can, these are hyperlinks, so you can click on it and it takes you to the relevant paper. So we started with MADE. This, if you recall, is, the conditionality and each output is conditioned, and we learned kind of in autoregressive model. The training is fairly quick, simple, at least it can be parallelized and so on, but, the challenge is that the data estimation methodology makes sampling quite difficult, and even for a simple data set like MNIST, you can see that it kind of sort of does the job, but not very great, because you can see the jitter in the resulting images. Then came pixel CNN or pixel RNNs, and when they were applied to 64 by 64 ImageNet, you can kind of sort of see something in the images, but again, not enough to recognize even the class to which the ImageNet's images belong. And of course, it's a big jump from dealing with 28 by 28 binary or black and white images to full color images. So the color does come out, but nothing in the classes can still be made out. And so along the way, dilated convolutions were introduced. We kind of touched on that, how WaveNet came into play and brought in the concept of using dilated convolutions onto 1D data, the fact that this could be applied to speech, and in fact resulted in commercial deployments of WaveNet by Google within like a year of the technique coming out. By the way, the same technique and some additional tweaks led to these video pixel networks where pass frames are used with convolutional networks then feed into an LSTM, which then generates an embedded representation. And those are used as conditioning information for a pixel CNN decoder that then generates the next frame in the video pixel by pixel. And in a sense, this was again a great progress because it was able to generate and produce coherent videos of kind of robots moving objects and so on. So a lot of work went into, as we'll see in many of the techniques that are discussed, a lot of some architecture and a lot of engineering work, which means, tweaking the batch size, tweaking the hyperparameters, and so on and so forth. And over time, a lot of effort into both the architectural innovation and better engineering gave us kind of the subscale pixel networks, the result of which you see on the left, and then the hierarchical autoregressive image models with auxiliary decoders. As I mentioned, each of these, you can click on them and they'll take you to the relevant papers, where you can see the quality of the images has now significantly improved. The classes are very evident, and so on. So they produce kind of coherent samples, and they are cleverly conditioned GANs. And these on the right use latent autoregressive models, and that's because of the vector quantization that we then discussed, followed by the pixel CNN modeling of the latent space. Right. So this is the variational quantization VAE that in the autoregressive model domain. So besides the domains we've discussed, which is mainly images and video, we all know that, and audio because of WaveNet, we all know that autoregressive models have been a huge kind of success in NLP. The GPT-2 success story, where it's providing a prompt, we are able to generate multiple paragraphs of mostly coherent text, which kind of seems to make sense and is related to the prompt. And that, to give you an idea of where things started, it's the history of language models and kind of the progression through the variety of language models that came up over time. N-gram models, and these were barely able to do any predictions, and very successfully at that, moved on to RNNs and LSTMs, at which point, we may be generating a couple of sentences or combination of words, and then along comes the transformer, which is able to generate coherent sentences, and then we kind of continue to increase everything about transformers in a sense, make them bigger, make them go from millions to billions of parameters and train for weeks on end and so on, and then resulting in the GPT-2 kind of results that we saw on the last slide of being able to produce not just multiple sentences but multiple coherent paragraphs. So that's kind of the entire history of autoregressive models in the NLP, which have shown the results of all the work that's gone in towards improving these models. Now, so if we then consider what has led to these advances, there are significant components, if you will, or significant contributing factors, larger batch sizes, which have enable us to get more stable training and stabilize the models, optimize the losses much better, and all of this because of increased computing. GPU sizes have grown, the CPU memory sizes have grown, and so on and so forth. Whenever we do sequential models, we are able to use larger hidden unit-based models, deeper models, which corresponds to more layers. All kinds of clever ways to condition, like we've seen in the whole GAN, as well as in audio and text. The pre-processing, and the couple of examples he gives are, in case of WaveNet, the continuous audio that is typically available to us as input is processed and converted into discrete entities. We saw that also in self-supervised learning towards the end. So there's some amount of pre-processing techniques that we apply to get these good results. Similarly, if you think about in the text space, we also do some pre-processing because we use, for example, in text, byte-pair encoding, which is kind of in between just character level encoding and word encoding. So that kind of that's what he puts into the bucket of how pre-processing helps us get better results. There's obviously been and continues to be a significant increase in compute power, and today's modern language models that are deployed are trained on multiple and distributed GPUs, no longer even on a single GPU. And as I mentioned, the Googles and the Facebooks and those who have compute power kind of train these for days, if not weeks, and that's the result of the models that they put out. The other interesting aspect is over time, we have been able to relax the assumptions and make fewer assumptions and have fewer assumptions embedded in our model. So for example, he talks about we need not only think of the pixels in image as being Gaussianly distributed, but we can think of it, as we have seen in some of the techniques, we can begin to think of them of some category distribution, and that works better with cross-entropy loss. So as we make progress in autoregressive models, it's also been because over time we have tried to come up with a theory and put into practice what would happen if we make fewer assumptions about the data. And then architectural advances, masked convolutions, dilated convolutions, the concept of transformers, all of these kinds of things, and also loss functions, and basically shifting as we did with fewer assumptions, then we can go or move to the domain of cross-entropy loss, which helps us primarily because this is something that's being used and tweaked, and the optimizers have all been heavily tuned to be able to do a good job with that kind of loss. So all these different contributing factors have helped us get to the results that we see in autoregressive models. So what is the future, if you will? What still lies ahead? And here he brings up a concept which at least I had not seen before. A lot of what we've seen is kind of data parallelism versus model parallelism is yet to come. Then something we touched on, which is, we have done GPT-2, maybe 3, and then these increasingly trillion parameter language models that then pretty much can train on the entire internet and basically ends up kind of compressing the internet's text into the model, as it were. And what also is a potential possibility in the future is having the same model for multiple modalities. So not just for text, but combining text and pixels, image and video, share the self-attention blocks, and do the compression of Wikipedia for text and YouTube, Instagram for images. And you can see both the power that models would have, as well as the demand for compute and the complexity of the models, right? So in this case, all you would need in some sense are just separate blocks of encoders and decoders. And you could potentially think of having same structure of the model, but having different kind of component building blocks for dealing with the different domains. Remember, sampling is really a struggle. It's, as we'll see in the negatives shortly, there's a need for definitely improving the speed of sampling. Otherwise, these models can't work in the real world, if you will. And so that means that there's a lot of low-level core engineering work that will necessarily need to be done. There's a lot of math, I guess, associated with that still needs to be worked out, which means new kernels with sparsity, efficiency, and I haven't kind of spent a lot of time digging into this, but he talks about, wave RNN versus parallel wavenet models which try to address the need for fast sampling with autoregressive models. And then you can release or make some of the autoregressive structure a less constrained, like we begin to see with when we talked about pixel CNN and so on and so forth, but train on a much larger scale. So these are parallel pixel CNNs that then begin to trade off some of the harsh restrictiveness of autoregressive structure, and the trade-off helps us kind of improve our sampling time and also make some independence assumption, because the autoregressive structure comes from the fact that there's a dependency that strictly needs to be imposed for the strict autoregressive structure in the models. And then new architectures, self-attention, and self-attention in turn kind of introduces some inductive biases, and it's an interesting way of looking at attention, which is, it leverages a lot of computation for each of the parameters that are introduced in self-attention based models. So again, these are all things that one could pursue further, or there is more work going on in these spaces when it comes to autoregressive models. And continuing the same topic, it's still an active topic of research. Keep in mind, obviously, the course is targeted towards advanced masters and PhD students, so kind of telling them what kind of domains are interesting to pursue. More engineering, especially from a sampling perspective, speeding up sampling as we saw, and also architecture design to do some of the trade-offs we talked about towards the end of the last slide. Need to support much larger models and bigger data sets. Success in unconditional video, audio, text, images, and combinations thereof, and then repeat of the sampling time engineering work that needs to be done. What are its negatives of the autoregressive models? Big one is there is no, in comparison to some of the other techniques that we'll look at later, there's no single layer that we can talk about that has the learned representation. So from this derives some of the other issues, such as the third one here, not directly usable for downstream tasks. That's because if we have a learned representation, you can kind of either choose to tweak it with fine-tuning or directly apply it, like we did with the self-supervised learning task where we learn representations. Here, there's no layer that, think of pixel CNN. There's no layer that represents the data that's learning, that the model is learning. So that's an issue with autoregressive models. Also, as I've been harping for a while now, the sampling time is slow for any practical deployment. And because there is no learned representation, there's also no interpolation. So you can't say from between this, give me something between a couple of classes in the data. It just learns the distribution of the underlying data. That's kind of what it does. So that's the reason that some of these restrictions or limitations of autoregressive models. So I thought this kind of an approach which kind of summarizes, hey, why is this model or these type of models good, what are its pros, what are its cons, and what work remains to be done is fairly interesting and a good summary takeaway that we can have from this lecture and almost, I would say, from the course going forward. On that note, I would mention something else, like if you actually go to the website and click through, there's also a midterm, and I thought, at least personally, I found the approach for the midterm of the course very fascinating. It's like a 6 or 7 page handout for the midterm, and the interesting way that the midterm is apparently, for this course at least, was delivered is, and he talks about it in the first session, is the questions and the answers are provided. And because they say, hey, we've kind of dumped so much on you that, all we want you to know is at least at a minimum, all these things you should take away. So the answers to the questions are provided, and those exact questions are the questions in the midterm. So they just want you to kind of memorize and learn, if you will, those answers that are provided. And I kind of skim through that, and it's fascinating because at least I think it gives you a very succinct mathematical and theoretical description of the techniques. And that's a good thing to go through as well. And if you can kind of take away this set of slides and those set of answers to the questions about each of the techniques, I think down the road, if that's all you remember, I think that would still be pretty good to come back and look at any of the details. If I would encourage you to print out, it's like 7 or 8 pages of the midterm and kind of go through that. Okay, moving on, we discuss next the same type of approach towards flow models and the progression of the flow models, its positives and negatives, and
Srinivas, if I may, couple of questions regarding autoregressive models I wanted to maybe discuss briefly.
Sure,
one
absolutely.
Is, about this cross entropy loss mentioned in the causes of the success, and but for images, didn't we had a problem with that because by using cross entropy we are kind of losing the structure in for example, if we treat the color intensities, binarized color intensities as or not binarized but binned color intensity.
Quantized.
Quantized. So what they did, they used this mixture of logistics, right? And that was worked much better, right? So cross entropy is not suited for all problems, or maybe we don't have a way to represent images in a such that cross entropy would be useful, right? So I was thinking about it, and another what I was thinking is that so autoregressive models, right? We just trying to predict next token or next element of a sequence based on the previous ones, and in images we don't have a sequential structure, and it makes it a bit like trying to use a tool which is not intended to succeed. So that there are like this engineering decisions which made it work better, like pixel snail, and so where you play around with this, like how do you treat how you select a context, right? But still in images we don't have this kind of sequential structure, so we don't have actually a previous elements of a sequence. We are just like, and probably that's so we were mostly focused in practice on this applications of after autoregressive models to images, right? But it at least to me, it looks like that's the least favorable settings for autoregressive modeling. So, and
yeah, no, I think on the second point, you're absolutely right. I mean, it seems, and I'm not sure whether down the discussions it comes up, but it does seem to me that that's why, or switching slightly, the CPCV2 is somewhat interesting because, as you say, it almost seems, if we just look at autoregressive as an example and its application to images, that you would want some technique which somehow is tuned or is favorable in its approach towards the modality it's good for, right? So autoregressive does really well in a word context because there's dependencies in a sequential sense, like words come in sequence as we talk or even write. But as you said, pixels in an image don't have necessarily that relationship or structure. So it seems like the structure of the space would determine or the favorability of an approach, right? But that's where the CPCV2 is interesting because they try to come up with a framework which can broadly be translated into multiple domains. So yeah, I think the second point you make about images not inherently suited, but I haven't looked at the video example they gave, but videos then ought to be a little better, the video prediction stuff, right? Because again, there is a sequence concept.
Yeah, that's really interesting. I guess maybe when we can handle video better in terms of computational expansive like networks, but I guess for example, for human learning of like visual concepts, this kind of temporal structure of what we see also is useful. It kind of, I guess, it makes learning more efficient, probably because we have some kind of sequence of images rather than a single image. And I believe I'm not sure where I heard it, but like I think that humans, I guess animals in general, more rely on the shape, right? And what we are doing, we are kind of scanning all the edges of what we see, and I think there is kind of not a single image that we process, but kind of this sequence of images that are strongly correlated. So,
yeah, I mean, the whole vision thing, I mean, you touched on it, but it's a much more fascinating aspect. If you dive into each of our senses, how they end up working, and it's almost incredibly beautiful in some sense, because it turns out that I read way back that the reason that the Impressionist painters had such an impact was because there is something inherently in our visual system that apparently the way we visualize images is, and I'm sure I'll screw this up, but I would encourage people, and if I can dig up the reference I'm talking about, I'll post it on Slack. But it's like they said that the reason the Impressionists became so popular and stuff was they touch on some inherent way that our system processes the images, and we just don't know it. And that's the reason that modern science has figured out that there's a step in our processing of visual images that the impressionists seem to have captured. And that's the reason that the impressionism kind of resonates so much with us. And I thought that was fascinating because the artist stumbled on something that scientists took a whole lot of more time to figure out why we find that beautiful. So that's fascinating in its own sense. But switching topic to, your first point is an interesting one about the cross-entropy laws. I'd have to welcome any other thoughts, but at least I'd have to go back and look at when we did the VQE, variational quantization stuff, and look at it in greater detail of, because his summary was, hey, helping to move to categories rather than treating things as a continuous distribution or Gaussian distribution helped and improve in the context of autoregressive models. Now, improvement is not kind of equivalent to the best results because, again, some other variation applied on top of cross-entropy might be necessary. But his comment was that when we started moving away from just a density distribution or estimation to category estimation is when these models were able to be applied to larger sized images, is what I recall. But your point of, cross-entropy still having challenges and that not being sufficient may very well be a limitation as well. So it might both be that it helped us kind of get a little beyond dealing with MNIST, but not a whole lot better may very well be the case.
Yeah, maybe given a sufficient amount of data and sufficiently expressive underlying function, I mean, a neural network like with a large number of parameters, maybe it's not an issue anymore. Maybe then cross-entropy can work fine, and there's a like this ordinal structure of categories is captured by the network itself, right?
Yeah. So thanks for bringing those points up. I think definitely pausing at the end of each of these segments and kind of discussing them would be a good idea. So let's do that once we're done with flows as well. Thanks. That's good. Any other comment from anybody? Thoughts? Okay, if not, let's move to flow models, and kind of here are listed all of the different steps that we took on flow models. And if you recall, flow models are, autoregressive models with a couple of other complications thrown in. My recollection is, hey, we need it to be kind of reversible. That's one of the things. And then there was one other constraint that I forget now. But we needed it to be not reversible, invertible, if you will. And then there was one other constraint. If anybody recalls what that constraint was, feel free to mention it. I just forget there was one other constraint in order to make the flow models work. And then obviously we've made, progress from where we started, which was nice, and then the real MVP all the way to Glow and Flow++ and so on. So in flow models, the MNIST results already were pretty good. You can see if you, since we just saw it compared to autoregressive models, these look a lot less jittery and a lot more clear. Applied to this facial data set, you can begin to see faces in here, but as we'll see shortly with GANs, nowhere near what GANs can do, but definitely an improvement, because I don't think the autoregressive models would be able to handle, at least the original models wouldn't be able to handle things to this extent. But then when applied to CIFAR10, you can just see blurry blobs, no notion of class, and obviously CIFAR10s are, if I recall, I think they are 32 by 32. And so, even on a small size, not much of good. And FVHN, nothing there again. But that's nice, which again, is 7 years back, eons in this space. Then came real MVP. Do not recall off the top of my head all the improvements that were made from nice to real MVP, but kind of beginning to see some better results. Kind of other improvements to flow, and then applying batch norm to flows. Those were kind of some of the improvements they made, and to make the models better. Keep making progress. This was Glow from OpenAI, and you begin to see this is, I believe, the celebrity data set and so on. Huge progress when you compare these or the originals to what is able to be achieved. Again, real MVP, right? Much larger, dealing with much larger images. And then, obviously, if you're in a Berkeley lab, you ought to highlight Berkeley results, which is the Flow++ models by, I guess, Peter DeBale's work or his lab students and so on. And you can see they were able to get for ImageNet 64 by 64 and a comparison of the non-autoregressive flow space. Remember, the lower the better for the bits per domain. And the first Flow++ models gives you 3.09, which is at least in the range of some of the better, although not besting the best autoregressive models. 3.09 is definitely in this range of, for example, gated pixel models, pixel CNN models, and so on and so forth. So that's, and not very far off from some of these guys. 3.69, 3.57, or 52. So begin to make good progress to where you can push the flow models to about where autoregressive models were, are. Comparing what is then left to be done. Obviously, big advantage of flow models is addressing the sampling challenge, right, which was a big drawback of autoregressive models. So the future work is, the masking work needs to be improved. Closing the gap, is it possible to close it even further, because these are close, but they haven't beaten the other guys. And then here are some thoughts, fewer expressive flows versus using shallow flows, multi-scale losses, and the issue of, do you go after very small bits per dim number, or are you more interested in the sample quality being much better? And interestingly, there is a trade-off apparently between these two spaces, somewhat akin to what we trade off even in GANs or autoregressive models between blurriness and quality. There's this whole issue again with autoregressive models and with flows where there's not, the concept of representation learning, which occurs in the latent space and with self-supervised model and so on, and challenges of initialization, which isn't unique to this. So these are all things that can still be done in this space. The other issue with flow models is, you use a ton of parameters in order to get any kind of good, or to get the kind of good results that we see with high quality images or megapixel images. If we recall anything from flow models, you should recall that there's no dimension reduction in flow models, right? So there isn't this concept of going to a latent space. If you recall, we kind of said X or Z is the same as input X, right? So that's like one of the limitations, that you're not dealing in any kind of a latent or space where there is a reduction in dimensions. Then conditional flow models require a lot of architectural innovation and a lot of engineering details. And for example, he says that for Glow, as a model, it requires something of the order of 500 million parameters to deal with the celebrity faces that we saw. And that's one of the reasons why, at least when you need high quality images, GANs are preferred, as we'll see in a moment. The summary is that in order to get to the GAN level samples, so GANs kind of set the bar, if you will, for dealing with high quality, high fidelity of images. And at the same time dealing with the likelihood scores, which the autoregressive models, as we just saw, give you much lower bits per DIM. So flow models are somewhat caught in the middle, in the sense that while they give you better results on the image, it's not quite the GAN level. And while they give you somewhat competitive bits per DIM, they're not quite at the autoregressive model level of likelihood scores. And then you have to worry about, getting stable training, and it seems very much ad hoc tweak your way to results than here's how you should do flow models. So not yet a fixed set of engineering practices in this space. The negative, one of them I already mentioned, the Z space is as big as X, so there isn't any reduction, which in turn ends up with the models becoming significantly large, 500 million parameters for kind of the celebrity faces thing. So there's no lower dimensional embedding, and we have to initialize these models in a very deliberate way. I remember there was this thing of using half of them flowing through, and the other half where we use the inverse and so on and so forth. It's a lot of careful work that needs to be done. Any comments or thoughts on flow models discussions before we move to latent variable models?
Yeah, one small thing. I don't know if this is a right way to think about it. So I was listening to the Machine Learning Street Talk podcast, and one of the discussions they always have is that any model that we learn is a low dimensional manifold in a very high dimensional space, right? That's one of the hypotheses or something like this. So here, when Z is as big as X, then we're probably wasting a lot of resources.
Yeah, a lot of parameters. Yep.
Most of Z is probably not much more than noise. So yeah, it would be very interesting if there was like some work that said, well, here's Z, and let's see how we can do a lower dimensional embedding, or like how we do with what they call it.
Almost you're thinking something like maybe pruning the network after some stuff is done, to where you can kind of begin to begin to chuck away significant chunks of Z, which aren't quite contributing.
Yeah, so it's almost like PCA, principal component analysis, where you find the dimensions that are very, very correlated, right? And then rest is probably nothing more than noise. So you could probably just take the mean and the standard deviation of the noise, and maybe if you have 1 million dimensional image, maybe just the first 20 or 30 are actual vectors, and then the rest are just noise, and you could really squash the. But yeah, I don't know if it makes sense to think about that kind of stuff, to change the dimension of the actual Z. But then we might actually have gone into the VAs without.
Yeah,
Anyway.
that's why I was thinking. I mean, maybe not screw with the way of generating Z. I mean, generate Z as big as X and then prune. But then, in pruning, what do you use to prune is the question, right? Like you say, we'll have to bring in other things like, I don't know, PCA or something like TSNE or other things, UMAP, blah, 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 and see whether they are able to prune any better. But then again, it's also a question of the whole thing hanging together. So if you generate, and then we'd have to obviously generate samples still and see whether the samples are as good if we pruned, or somehow they introduce other artifacts. But that's kind of fascinating
possible
space to play in.
Because we have this in flows, we have this prior that our Z is, for example, uniformly distributed or Gaussian or whatever. So we impose some prior to and map the data distribution to this simple distribution. And how can we prune without losing this properties of the distribution we map to?
Yeah, no, I think.
Good.
It's a good question.
I think you could probably have a function that takes that that turns it into another embedding, and then another inverse one that takes it back. It's like a slightly lossy version of it, but minimize the compress. It like basically is like a compression. You take the high dimensional structure of it, you compress it.
So
or
in this
yeah,
way, we on the autoencoder, right? So, and probably this work we briefly discussed by Max Wallin and collaborators on surjective VAEs, where they merge the flow models and autoencoders. I guess they have some ideas in this direction, maybe. So I guess that is kind of ongoing work, and maybe if we will check out some publications that coming out from that group and related publications that would give us some understanding. But in general, I guess the idea is like to merge this properties of autoencoders and flows, and in this way we can get something that will be on par with GANs. So that is one of the directions related to this topic, I guess.
Okay, I think I saw the paper. I posted it. I think that's the one, right? The survey flows, surjections to bridge the gap between VAE and flows.
Yeah. I guess it's that one, and yeah, I saw. I haven't read the paper, but I saw some. I think I've posted a link some time ago in our Slack to this workshop with Max Wallin, and I guess there is a bunch of people working on the topic, and in that workshop he had a list of references with different kinds of VAEs and things in between of flows and VAEs, I guess. So yeah, that's.
Yeah, and one disadvantage he mentioned, because Z is as big as X, scaling becomes a problem, because the larger the input X, the larger Z gets. So that is a challenge as you begin to deal with larger and larger images and so on. Okay, latent variable models. Again, as I mentioned, I don't think they discuss wake sleep too much, but if at all. Then the approximate likelihoods, variational lower bound, the VLBO method, Jensen's inequality, just to refresh our memory, how we got there. Then, the importance weighting, then the pixel VAE, and then the variational quantized VAE, which we touched on already. So those are the latent variable models and all the improvements we made to them over time. And this is an indication of the, way back again in 2013, 8 years back, kind of figuring it out and applying it to MNIST, and then you begin to see how smoothly the thing goes from a 9 to an 8 to a 6 or a 5, and the transitions, the slopes, variety of things having to do with MNIST, much more kind of coherent samples, able to interpolate from point A to point B on the due to the representation in the latent space, able to scale very well. Kind of this is pixel VAE applied to the bedroom data set and so on. Kind of hierarchical later inference producing the next set of improvements for our models, and therefore, again, compared to autoregressive and flow models, you can begin to see the appearance of classes with respect to ImageNet. So much better when applied to slightly larger images. And there's a whole set of application. This is, when applied to the faces, again, the relevant paper reference for this kind of model. And then here are the applications of VAE in different domains. And the sketch RNNs, I'll switch to kind of play the video and then comment on the video. So let me know when you see my screen switch, if you will, because there's an interesting, I'll stop sharing this guy and share that guy. Are you able to see?
Yeah, video.
The generated query networks. Okay, good. So if I play this, so just to set it up, I think this was DeepMind, and apparently this is use of autoregressive to produce video synthesis by taking in kind of couple of provided views of, if you will, this space that you see on the left, and then embedding that space into a latent variable, and then interpolating that latent space for a query view, right, across multiple possibilities. So from, these little things are a person's perspective, if you will, I guess. And then from a first person view of, or your pose with respect to this space, you are kind of able to then query what the view would look like and predict that, and thereby learn by comparison to the ground truth, right? So through this kind of synthesis, it's, an agent can kind of learn through variational inference. So this is a very practical use of the kind of architecture, right? Because you're able to learn, an agent can learn about a environment. So it just kind of portrays the sequence of steps, as we'll see in a minute. You want this add. Okay, so that's that. And I'll stop sharing that and switch back. Of course, I haven't gone and looked at the specific paper, but it's kind of a fascinating VAE application, if you will, that they illustrate. And the appealing property of VAE, its advantages is the thing that we have lacked so far in autoregressive or flow is this compressed representation learning, right? So it gives us something that we were lacking till now. It continues to give us the approximate log likelihood, so we also get that. Then, one thing, I don't know whether I highlighted in the previous two techniques, but I mentioned it in the autoregressive models, is there's no inherent, because there isn't a single layer that represents what the model is learning, there's no interpolation possible, which I definitely mentioned, but there is another drawback of the two techniques prior, which is how do you retrospectively analyze what the model learns? In a sense, this touches on maybe what Otto was pointing out with respect to what I was mentioning as pruning is you can prune if you kind of have some ability to retrospectively analyze what the model learns, but when you don't and you're just kind of mimicking the underlying data distribution, then you don't have any inherent information by which you can analyze what the model has learned. And because of that, kind of interrelated with that is the fact that you can't interpolate. Whereas as we saw in even the very first MNIST Kingma 2013 paper, we are in the MNIST latent space able to interpolate between two digits, which neither flows nor just the autoregressive model is able to do. One other thing which I believe touched on in this space when we looked at is this concept of disentangled representation. That is, in the latent space, try to find variations whereby, and the example I keep in my mind is this smile versus not, frown versus not, by kind of parameters or tweaking things, we are able to kind of make a person smile or make a person frown by the, eyebrows and mouth and variations in that, for example, and that's the whole concept of disentangle. So if because we go to the latent space and then in the latent space, if we're able to kind of disentangle those things, then we can potentially find dimensions that we can then vary, which then results in variations in the model. So the net of the VAE is it does four things simultaneously. One, it's able to generate models. It's able to generate or continue to give us the density. Because of the latent variables, we can kind of do this interpolation as well as retrospective analysis, and it reduces the dimension and is able to potentially do this disentanglement. So unlike the previous two, it kind of gives you all four of these capabilities. Now, what are some of the disadvantages? Blurry samples. We saw that already. They don't inherently result in really good models. There is a lot of blurriness in the output, and therefore we need more powerful decoders, or as kind of Art already hinted at, we are limited by the Gaussian posterior. So what better posteriors we can use is something that we obviously will need to further investigate. Large scale, unlike GANs, is still not quite at the level of GANs. While there is this concept of disentanglement I mentioned, and remember that with the VAE, we have two terms, right? One is the likely, one is the not likelihood, I meant to say kind of the representation term. The other is the KL term. That's kind of what we end up with as the loss function. And so it's playing with the KL term that gets us towards this disentangling in the latent space. But this disentanglement that people have shown is only practical in kind of toy domains, not in anything that would be substantially probably applicable in the real world, practical. And the point is that while this method does 4 things, as I just mentioned in the previous slide, all of those 4 things, it doesn't do any one of them the very best. Unlike, for example, let's say GANs, it just quality really the best. But in this case, you can get close, but have issues. So it's the fact, the big advantage is you can get all of the above. You can get the likelihoods, you can get the disentanglement possibility, you can get, good quality, but not the best at any single one of those 4 things, if you will. Right. So it does all 4 things reasonably well within the same framework. So this is where Andre also mentioned cross entropy based and then weakly autoregressive. So you begin to release some of the strict autoregressive nature, improve the decoders, use pixel CNN and whatever pixel snail, blah, blah, blah. More powerful posteriors rather than just the Gaussian, hierarchical latent variable models to learn at the coarse features and the fine features and begin to kind of interpolate between them. This is especially true when we dove into it about, facial features and then hair and very fine-grained features, as well as big features with respect to, male or female faces and things like that. We still need to do work to prevent, and this becomes a bigger and bigger issue as we get into the later models, prevent the posterior collapse while using pixel-like decoders and scale at the level of flow models training. So what that says is, while VAE is pretty good at multiple things, we still have work to do to get it to be the best at everything. Any comments or thoughts about VAE before we move to implicit models?
I have a question. If anyone remembers this disentanglement because of KL divergence, I believe we discussed it during this VAE lectures, but I don't quite remember if it's theoretically kind of inevitable, or is it just some kind of phenomena that was empirically discovered, and there is no strong theoretical evidence that disentanglement should appear in this latent space when using VAEs. I think it was a beta VAE paper, right? That was talking about this stuff. I don't remember.
Yeah. Well, the short answer is I don't, but the comment I would have, Atu, is I don't know that there is an answer to, or at least I don't recall the answer to the specific question which you posed, which is, should it emerge from? But what I do recall is it does, meaning disentanglement. What I do recall is they do show that it is related to the KL divergence space, but does that doesn't answer your question of, does it therefore inherently, is there something showing that because of that KL divergence term that it should inherently emerge? I think it was discovered and then found to be linked, but the inverse is not true, right? Which is that because it happens to be related to KL, there is nothing I've seen which says it must emerge from, or at least I don't recall it. But I do recall that they, I believe, showed the relationship that it's not related to the representation similarity. It's related to this scale divergence portion of the loss.
Okay, thanks. And another question, if anyone remembers, so talking about scale and autoencoders, so this Wally model, or DALI, sorry, DALI model by OpenAI, right? It is kind of similar to autoencoder. If anyone remembers what was the reconstruction loss they were using. I'm talking about this model that generates images from text, and what they do, they basically apply this like VQ VAE approach, but the texts and images were embedded in such a way that these latent factors are matched between description, text description, and the image itself. And then in such a way we can generate images from text, right? We convert the text into this latent representation, and then we use it to feed into the decoder and generate an image. And so they have like really impressive results from a point of view of both content and quality. But yeah, I believe their nice results were also like there were like another model that was ranking the generated images. So the best images are looking really good, but not all of them. And if anyone remembers what kind of loss, reconstruction loss was used to get that working.
Anyone?
Yeah. Anyway, I think that that might be like an example of scaling up this this kind of approach, right?
Yeah, definitely. I haven't looked at it. I think I but that'd be fascinating to dig into it. I haven't looked at that paper. Thanks for the reference. I'll kind of look at it. So the final, well, not quite the final, but the next to final implicit models, which is the GANs. And then we obviously spent some time looking at, the concept of moment matching, which kind of push GANs a little bit further, mapping noise to data. Towards the end, we kind of looked at these two improvements or variations of the basic GANs. It all started with Goodfellow in a restaurant talking about, oh, this ought to work if we did the kind of generator discriminator two-player game, kind of very basic faces, but then when applied to anything in the CFA space and stuff, pretty much incoherent blobs of color. From there, DC GANs kind of getting us the sample qualities for the bedroom data set much better. And then moving on to style GANs. And this is where the coarse and the fine styles come into play as well. And then you can see Big GAN begin to generate very smooth interpolations, fantastic images, quality, all that kind of stuff that we spent a lot of time trying to figure out, a large amount of training stabilization picks and techniques, and photorealistic images, right? So the place where GANs are at with respect to the quality of the images and the results they produce is just unsurpassed by any of the other techniques, at least at this point. The future work, though, I think is the fact that, they still struggle because of mode collapse, and they kind of trying to, it is hard to predict against GANs. Today, they are kind of the state of the art to produce the quality, high quality images, but unconditional GANs are still work in progress. Fine grained details are an issue, more complex scenes, and especially because of this mode collapse issue, generating self-driving video, dealing with self-driving cars, what it visualizes, complex scenes with people, bicycles, cars, multiple people, multiple cars. That's kind of still not what it can do well and consistently well, keeping track of multiple things at once in light of mode collapse. So there's a lot of these kind and related topic of video generation with that level of consistency. That's all still a work in progress in this space and lies ahead in the future. Other kind of engineering work, if you will, we've kind of touched on the Lipschitzness constraints, but is that the only thing, or can other new mathematical approaches be found? Feeding in noise at the different levels, we continue to see, like batch, and then this whole instance normalization that they introduced in one of the papers. I forget the name of which one, but instance norm, and then subsequent improvements got rid of the need for that. Architecture design, upsample, downsampling the images, and then the different trade-offs. Are there better losses? If you recall, we also began to use hinge loss in one of the variants. Stability and scalability, meaning much deeper models, fewer parameters, larger batch sizes, and then beginning to introduce the perturbations. Again, one of the things that StyleGAN did was get rid of instance norm and then provide some noise. So it's the balance between, or the improvements in coarse and fine interpolations in this space. These are all things that are still very much work in progress in the implicit or the GAN space, right? So training them consistently, improving the architecture, a lot of tricks having to do with dealing with them in the space of bigger models, but with fewer parameters. All that is work that lies ahead. What are some of the negatives? It does appear that the extent of engineering tips and tricks and details you have to pay attention to get the GANs to really do what you want. I still remember, even with DC GANs, which are simpler compared to the big GANs and style GANs and big GANs and all of that, Jeremy kind of saying just before he went into the lecture, he was like, I'd been struggling with this for days and nothing was working. And then, an hour before I'm to get into class, the thing begins to generate really good results. So, an indication of the extent of work that is needed to get GANs to reliably produce and consistent results. And then had to know which piece is pushing the edge in the various ways. It's kind of related somewhat to what we touched on, right? Like what Atto was asking of, do we know there's any theoretical basis for why KL divergence loss rather than the reconstruction loss is thing which helps us disentangle? And at least this generic comment seems to say, well, the theory of GANs is not yet fully understood. Ablation, given everything, even to set it up and get it working is hard, then tweaking it to get the results of holding everything constant and getting one thing to work is incredibly time consuming. There's always this mode collapse challenge. Another related challenge to GANs, which we touched on at the very basic start, is there are some metrics, but they are far from perfect and far from enabling us to do what we really need GANs to be able to do, and because they do multiple things, and it's there's no inherent metric which captures all of those things in one entity. But keep in mind that as we discuss this, while they are dominant in our discussions of GANs, the fact that there's a lot of engineering details and a lot of pieces is not just true of GANs, and that is, I think, fair in some sense. While we talk about GANs much more or talk about the engineering details of GANs much more. I think personally it's because GANs just stopped working, whereas at least with VAE and other stuff, you can get some results, but the quality of the results may not be good. But in case of GANs, you just get noise, and that doesn't lead to anything. So it is the case that even in VQ VAE and other VAE, important weighted VAE, you do need to pay attention to details. Maybe they still produce some results, which is why we seem to think that for GANs, the engineering details are super important. But it's the case that they are important even for the other methods. Before we go into comparisons of GANs and the density models, any other comments with respect to GANs? I think one other thing he says, which is true, is GANs have become so dominant, partly, I think he touches on it in the next set of slides, but because, forgetting about the theory, because they are so good in generating the outputs and the desired results, artists and a lot more of the people who want to use GANs, who want to put it to uses and don't really care too much about how they work, have kind of taken it and really pushed it into spaces that are very fascinating. So that's a big momentum towards increased use of GANs by people not in the domain of machine learning and generating a lot of usages for GANs. Any comments, thoughts on GANs? Okay, if not, kind of comparisons of GANs and density models. This is something that I just mentioned that, while the inherent thought would be that GANs need a lot of handholding and it's just super engineering complexity, it's not just GANs, it's also true of other models to get them to work at the level like autoregressive model, but to generate celebrity faces. I think the extent to which you need to pay attention to multitude of parameters and tweaks and details are as much, if not quite the same. They're in the same ballpark. So it's not something that one should hold just against the GANs versus the density models. This is something we'll get into in a little bit more detail, that the theory of GANs and, kind of related to other questions, although he asked it in the context of autoregressive model, is how much do we understand them and how much do we say, hey, does the theory predict X, A, B, C will need to happen if we tweak this, or is it still very empirical that we do it and it results and therefore we know that that's what we get. But this is something that I think we'll touch on in a minute, that very often, and there are some very good examples, theory follows practice. It's not always the case that you come up with the theory first. Unlike in Einstein's prediction, which is what makes his prediction even more incredible, is the theory came first and then they measured that, oh yeah, gravity does bend light. But, seldom does that happen. More often you measure the fact that, there's a gap and then you don't know why and you apply things and then you figure out the theory. This is kind of saying GANs and density models you can kind of compare. Autoregressive models are blurry, as we talked about, and there it's saying that this trade-off between blurry and then the improbable models versus model collapse is kind of similar to compression at the cost of sample quality and then sample quality at the cost of missing mode. So there's some trade-offs, inherent trade-offs, which seem to be similar in both these spaces. And then he talks about, besides this supremely good quality samples, GANs are popular because they work well with huge images, and he gives some examples that, for example, autoregressive models, in order to work with megapixel images, they had to train on 512, he says, I think CPU cores, but it could be GPU as well, but, contrast that with few hours of training for a GAN on a single V100 GPU. So in order to be able to produce a good autoregressive models on a megapixel image, you need to have humongous compute, whereas, while a V100 GPU is still significant, but you can kind of get hold of it relatively, the complexity is not so much, or the compute needs, I should say, is not as high. So GANs can do things at much better quality at reasonable compute, not the same for density models. And then the same point in a different way, not just the compute, it's also the complexity or the size, and it takes a lot more time. And the point I mentioned that a lot of adoption by artists is another reason that GANs have been pushed forward into spaces that many more people are familiar with and are actually using it. This is something that I just mentioned, which is the fact that GANs, while people might criticize it because, oh, the theory doesn't exist, it's kind of empirical, people just kind of try things and nobody understands why it works. Here's Jan LeCun's examples of where this was true of so many things in life, like over the history of technology, telescopes came before optics, steam engines were invented and put to use because before the laws of thermodynamics were discovered. The airplanes, the Wright brothers kind of flew before all of the Bernoulli equations and the wing theory of wind and how it flows over the wings and what causes lift and all that was formalized, if you will, and so on and so forth. But these are just a variety of examples where to illustrate that theory often follows invention. It's not as we think that the theory comes first and then the invention follows. This is an interesting slide because it gives you kind of the taxonomy of remembering or recalling what we've learned so far. You have the likelihood models, go to explicit densities, and then you go into the flow and the tractable densities, so autoregressive and flow models, and then the approximate ones, which are the variational models. This is something we did not study in the course, and he says so. This is, I think, also not something that we look at in the course, but primarily he says that these two aren't discussed because they are no longer much in use. And it's what's popular and what's kind of the focus now. That's very much what we have discussed so far in the course. Right. So it's a good taxonomy to keep in mind of, what we went through so far. Maximum likelihood, then explicit density, flow, and autoregressive approximate density, which is all the variational autoencoder stuff, implicit density, which gives us to the variations in GANs. And the next two slides are also kind of very useful tips of when to pick which tool and for what purpose. So if we look at density models, then here are the things to keep in mind. If you only care about density, and we already kind of saw it from the pluses and minuses, and you don't care about the sampling, you go for autoregressive models. On the other hand, why? Because obviously sampling time is, a pain in autoregressive models. But if you care about sampling time, but again, not too much, because if you care it too much, then you probably not use this technique. If you don't care too much, a little bit, then it's still fine to use autoregressive, but use smaller models, and then kind of recurrent neural networks or convolution or self-attention. If on the other hand you can't afford this linear scaling, remember that in MADE we kind of strict autoregressive to T, we need to kind of depend, every successful pixel generation is conditioned on every pixel before it. Then if you can't afford that, then go for parallel pixel CNNs. The additional comment he makes, although I don't quite know that we dove into it in much detail, is the fact that autoregressive models are, while the examples they've used is mainly in the discrete space with pixels, he says that thinking that autoregressive is only applicable in discrete is not quite correct. And there are some, and I haven't looked at the sketch RNN example that he talked about or the world models. So because of that, I think we should not take away from the class, because I don't think they discussed these two papers in the class. So because of that, at least I would have taken away that the pixel CNN and all that is mainly used in a discrete space, but he says that's not true. It can be used for handwriting recognition, sketch-art, and world models, and so on. So I guess we'll have to dive into these papers to really broaden our thinking about how autoregressive models are used, not just in the pixel discrete space world. Then flow models, good for modeling densities and in this space of continuous valued data, and getting better for discrete pixels. And you need the larger models for complex data sets. And of course, sampling is much better. So you want both representation and sampling, you just want to try the simplest thing. Then variational autoencoders with this factorized decoders are more of a first choice for you. So in that sense, it seems like of these techniques, the flow models seem to be somewhat lagging, limited. But then again, as with research in multiple domains, things push along on the other space, and along comes somebody who works very hard on something that's been neglected for a while, and suddenly that becomes applicable in some space. So that seems to be the case for flow models at this stage of their evolution. When do we use GANs? When we really need cool samples, high quality images, large images, spaces, buildings, when we want class conditional models, as we've seen, then image to image translation problems. And if you want significant perceptual quality, don't have a lot of compute, as I discussed, autoregressive models need a lot more compute to get to the quality that GANs get to relatively easily compared to the VAE models, right? So that's when you pull out GAN, when you need cool samples, and all of these domains or all of these things are things that you care about. Any comment so far on these last few slides? Any thoughts anyone wishes to share? Okay, then if not, brings us to this last couple of slides, last couple of lectures that we spent time on, self-supervised representation learning. And this is, learning from observation, and also because we now have representations that we learn, they are useful for downstream tasks that aren't directly, that were kind of a challenge with some of these previous models. We can use it for classification, we can use it for object detection, segmentation, kind of use it as a backbone. And we use kind of data compute as well as core principles from each of these spaces to come up with these common sense tasks, right? This is what we studied in the last two lectures. So here's kind of the path that and how quickly the self-supervised space has improved over, I guess he says, probably the 2+ maybe 3 years up to 2020. And I'll talk a little bit. I looked at what is the state of the art today, even in the 2 years since the course was taught. So it, recall that in about, I guess, summer of 18, CPC 1, the classification, this was around 48.5 or 48%. From there, it's come with simpler at the time of when the course was taught, which I believe is spring of 2020. So we are about, 18 months away. We are in the fall of 2021. So this was spring of 2020. So let's say 15 to 18 months down the road. But 15 to 18 months back, this was 76.5% in terms of the top one accuracy on ImageNet. So from 48.5 to 76.5, and this was simpler. Subsequently, and if you do a quick, I think papers with code search of the state of the art today, the state of the art results today for something called ESVIT. I think the VIT is visual transformer and some combination with some SWIND. I haven't looked at the details of the paper, but the top one accuracy now is at 81.3 with MoCo V3 top one accuracy at about 81%. The Dino, which I think R2 maybe you worked on or looked at, you posted some reference to the paper, that's about at 80.9. Sinclair version 2, which we touched on in the class itself, is at 80.9 as well. So, from this 76.5, we have gone up by another 5% in about 15 to 18 months, because as I said, the ESVIT number today is 81.3%. And the MoCo version 3, MoCo version 2 I mentioned in the class, but MoCo version 3 is at 81%. And Sinclair version 2 is at 80.9%. So even compared to this 76, we have kind of pushed it up by another 5%. So summary of contrastive learning, it's actually, we spent a lot of time, it's kind of looked at as a dictionary task. And there are two variations. One is the predictive coding, which is the CPC V2, as opposed to this instant discrimination, where we do kind of compare lots of negatives, generate positive, negative instances, and discriminate among them. There are two ways of doing this dictionary lookup, if you will. The end-to-end, which is kind of what Sinclair uses, and then the momentum stuff, which is what MoCo uses. And then obviously, as the papers or the teams began to compete, they kind of began to borrow from each other. On predictive coding success is the CPC V2, which one of the lecturers worked on and produced much better results than V1 and closed the gap, if you will, the first time compared to supervised learning. And then momentum, contrast, and Sinclair, which we just discussed in significant detail towards the end of the previous lectures. So what are the advantages, disadvantages? Hey, one of the big advantages of CPC V2 is we spent our time on it, as I mentioned earlier today as well, is the fact that it allows you to set up a framework and then use that framework in audio prediction, in video, in images, and in text. So apply to any modality refers to these kind of 3 or 4 modalities and domains. And the beauty of it is you don't need to know the underlying variances in the domain. So you don't need to kind of know much about audio, much about how to augment and or change, because remember, we also discussed that, hey, the type of augmentation needed for unsupervised learning is different, because what you're trying to do is make the object, and Otto gave a very excellent example of this, which is, we inherently see objects in so many different orientation with respect to ourselves that we are able to build a consistent invariant representation of an object, whereas that's not something that inherently happens when we learn in these kind of environments. So in principle, it can be used to train a latent space generative models, and this framework is easy to adopt for all these different modalities. The huge disadvantage and pain in the butt with this method was, you needed to do all this patching, putting together, so you can't use the same technique for training and inference, because, for training, you're patching it up, so the model needs to be different when it comes to inference. So now you're then pushing a lot, while the framework is the same, you're pushing a lot of hyperparameter choices and all these kind of how far, if you recall, we said, 12 works the best. When you go to 16 steps away, up to 16-step prediction, then your ability to learn good representation drops. So there is, this kind of like, hey, it improves and then it begins to drop when you go to, when you move along in your stride. Patch sizes and then non-overlap, all these kind of challenges. You need multiple forward passes if you're using smaller images, and then it becomes a challenge to predict on bigger images. Batch norm, when you chunk, is hard. This whole chunking thing or splitting it into patches is a big pain in the butt when you want to do everything in parallel for TPU-like hardware. So while conceptually easy, its implementation hard, a lot of details you have to deal with because of the way the task is structured, which is a benefit because the same structure can be applied to multiple modes. So that's kind of the plus and minus of CPC-v2. Now, when you look at it in a MoCo sense, hey, it's a simplistic design. You don't have all these challenges of patches and having to do something different for inference and worrying about all these patch hyperparameters and how far you go and all this. It's just very simple. You can use the same thing for training and inference, no change in architecture. You can just use the same model for downstream task. The invariance distillation is very simple. You just need to augment, and this makes the pre-training look very much like what you would do in a supervised learning environment. But be careful, the type of augmentation you use aren't quite the same. The momentum encoder, unlike Sinclair, it kind of decouples the patch size, because the patch size you don't need, because of momentum, and it's storing it in that kind of buffer. You don't need all the negatives to be stored to be from your batch, and which means the batch size is independent of, is made independent. So that helps us kind of reduce the compute needed. So you don't have the link between number of negatives and batch size. The disadvantage is you have just pushed some of the problem onto this whole momentum update hyperparameter, and how much and how actively should you decay, because you now have this momentum, but how much decay should you use to bring in negative samples which are somewhat related, because keep in mind that if they are completely unrelated, then that is the reason for this fall off when you take samples from way down and there's no mutual information overlap. So you do need the mutual information overlap, which in turn means that you can't just arbitrarily put into buffer and not have any relationship between the images you are trying to classify as positive and negative. And now that you have this two things which are similar and unsimilar, you need to kind of figure out what is similarity, and the similarity may not be the same in all of the domains. So you're back into the problem of saying, oh, I can't do the same thing for text as I do for audio and video, which was one of the pluses of CPC. So there are different trade-offs, and if you understand the techniques, you kind of say, oh, I gain some, I lose some. What do I gain and what do I lose? And here is the list. Simpler, again, same thing. They, instead of using the momentum buffer and stuff and having momentum, they just said, let's go end-to-end. Obviously, you'll immediately recall that means that they are dependent on the negatives being in the batch, which means batch size is going to be huge. That independence in MoCo has been eliminated, but then at the cost of huge batch sizes. And then again, the same advantage as MoCo, you don't have to worry about, or you're in the same space for the model used for downstream tasks, as well as the invariance is the same, or take the same approach for as for supervised learning. Don't use the memory bank, and literally looks like supervised learning. We talked about the disadvantage already. It needs the large batch size. You kind of introduce the coupling again to negatives, and being in the batch need a lot of TPUs. And again, the same thing. Neither of MoCo or Sinclair you can easily translate to other modes, other modalities. Right. So the future, given where we are, or where we were, because I don't know whether some of this has been completely addressed with the CSVIT and stuff, but completely close the gap between self-supervised, supervised. And I don't think, I do know for a fact that this last thing hasn't been addressed, which is, okay, if we want, okay, we have achieved the goal of self-supervised, let's say for classification, it's at 81.3, and that's as good as supervised. But we do know that we are doing that by throwing a whole bunch of data augmentations, significant amount more of compute, and a huge amount of training time. So what if we said, oh, I don't want you to get me the results of self-supervised to be equal to this, under no constraints on this, but I want you to get these two to be equal under the same constraint of these three. That's the next problem to go solve. That is, how can we get equal results, self-supervised, supervised, while keeping the compute, data augmentation, and training time similar at least to supervised? So that's a big challenge, and it'll be fascinating to see how or whether we get there, or whether this is a trade-off that can't be bridged. But that will be a fascinating I think, space to work on. And then obviously the other element which is there is some of the tasks, and we already saw that benefit. Classification is a simple one, but as he pointed out, that's not the only one. You kind of need to apply, take the backbone of representation learned here, apply to, say, detection, say, segmentation and stuff, and then see whether you can get the same results as supervised learning. And, this necessitates, as we already discussed, that the objectives which are more correlated with the downstream tasks rather than just classification may be required. And then we are still dependent to a large extent on ImageNet, like a large curated things like ImageNet, even if labels aren't used from the ImageNet. But the ideal world, we would not even care about curated data sets like ImageNet, just take a large set of samples in a certain sense, like we do in the word domain, if you will, or the language domain. Just the dream of supervised is to just learn from raw data. So just pick up any images you find on the internet or pictures and, I don't know, Google Photos and that people have stored, and then without any filtering, and then just learn from it and be able to do all the downstream tasks. That's kind of the dream, at least in an image world. And then you can kind of extrapolate it to all the videos in YouTube and all the pictures on Instagram and so on and so forth. And the next thing is, I'll just switch again. Let me know whether you can. It kind of explains why all this is fascinating, because eventually what we are after is trying to build, if you will, for lack of a better word, these are my words, he doesn't use this for obvious reasons, but common sense about the environment that we exist in. But it's beginning to be built in the imagined world of games and so on. And for that, let me see whether I can get to share the give me a minute. I'll play this video. Yeah, that's the one. Okay, can you see my new screen now, which says future of self-supervision?
Yeah.
Okay, so let's click on that. Oops, what's happening? There you go. So let me. Sorry, let me switch again. So the idea from that video was just to say that, in a Quake 3, the characters are able to kind of make sense of the environment, the walls, the fire, the bullets, kind of parse the scene and interact with it, what is happening, separate objects from non-objects, and all of this kind of stuff. And the thinking is that it does a lot of it at this stage with still kind of looking at the pixels. The goal would be to not look at it at that level, but to kind of look at it at a semantic level, and that in turn is the future challenge in this whole machine learning space. So, look at it as pixel space is hard. Intelligence agents need to be able to reason over long horizons very quickly, build internal worlds that are on an abstract space, and the abstractions in turn must capture very useful things and ignore noise. So if you can read this for yourself, but what he says is, if you use pure RL, which I guess Arto and Mike will be teaching in the next 2 hours, is if you train to drive a car, it's going to have to crash into it 340,000 times before it figures out. And instead, what is needed is kind of the internal model of the world, so you can simulate the world much faster than having to bang your head 40,000 times into a tree before you figure out how to move into a world that has trees. And the guy asks, how do you make that? And, Yakun's response is, that is, in fact, the most challenging thing in AI and machine learning today. So it kind of captures what that video seems to show, which is, hey, you can do it. You can now do it in kind of made up worlds and constrained environments, but doing it in the real world and building up an internal model of the world. And in fact, this proprioception thing we started with is very fascinating, because the internal model is not just a model of the outside world. Sometimes you need a model of your models, and that makes it very fascinating topic. So self-supervision, you kind of, we have had that in the image space now, had it for a while in text. We have been able to do transfer learning. He says, at least at that time, there was next to nothing, although I think given the focus of Abil's group and stuff, I'm sure, and we have a lecture coming up on reinforcement learning. And so this is a big topic, mainly because we need to build this up in order to attack or make progress towards the big challenge, which Anlukan discussed. So I think we end back where we started, which is to say, hey, we really need to address this self-supervised learning situation. Before everybody goes, we've kind of fortunately finished in one lecture this particular aspect. I missed, for whatever reason, the semi-supervised learning as the next 2 lectures. So just a heads up, Motin, there may be some push out to your compression stuff. It's not the next topic. If anybody wishes to take semi-supervised learning topic, I'll be adding that to the calendar and schedule. If nobody signs up, then I'll do it. But if anybody else is willing to kind of go through it and take us through it, that would be great. So just keep an eye on the changes I'm making to the schedule. But that's it for today. Any comments or questions left over?
Thanks, Srinivas. It was a really nice overview of what we learned so far. Well done, really.
Thanks. Yep, I thought it was a useful lecture to kind of refresh ourselves. So the 4 things left are semi-supervised, followed by compression, which Mochen has signed up for, thankfully. Again, the text thing, Sujit had signed up, but I think he's kind of dropped off. So if anybody wants to do the language, which is a guest lecture, that would be great. And then I think, thanks, Sato, you've already signed up for the reinforcement learning part of self-supervised. So those are the 4 things, big things that left, which we'll examine over the course of the coming weeks.
Yeah, if Sujit won't be available, I can do the language lecture, but maybe he'll join. So
Sujit just dropped off. He said, dropped the note. Yeah. So if you would like to take that up, that'd be great.
Oh, so Sujit is will not be taking it for sure, right?
Yeah, he told me he's not doing it because he wanted to keep track, but he dropped off and never got back on. So he wants to excuse himself from doing that. So
Oh, okay. So, all right, so then I can do the language part.
Great, that'd be awesome. Thank you. Okay, folks, hope that was a quick summary and comparison, and at least I took away a lot of like the pros and cons, and it was a good refresher of all of the things we've gone through. Thanks, everybody. See you all next week. And look at the schedule changes that I'll be making.